if I had to write a book about this next topic, and I wanted people to actually buy it and read it and get excited about it, it would look like this. It would be called Beyond the Elastic Limit. Right? And that would kind of draw your eye in, and then you want to come in and read the subtitle. When rigid objects are pushed too far. My Doobie Keeper. That's my nominate Doobie Keeper. Look for it in bookstores. So we're going to think about is, what if we keep extending and extending and extending and extending? What's eventually going to happen? Let's look at the stress-strain curve. Stress-strain curve. That same one we just drew. We said, oh, they're usually straight like that. Yeah, they usually are. They're usually straight up to maybe 1%. That's not straight. That's not straight either. They're usually straight, and then other things begin to happen. Then they go from straight to kind of curved. They don't quite stay straight anymore. Right? And then they go into a third region where then really weird stuff happens. Okay? And these different regions are kind of mixed together. People call them the same thing. It's kind of people's notation and stuff. So let me just show you what's really going on. Where it makes a line is called the linear regime, as you can imagine. And that's simply for a small enough deformation, everything is going to make a line, except fire. And every polymer. And all metals, anything crystalline or polycrystalline is going to make a nice little line in the linear regime. So like, just like a spring. But then if you go too far, it begins to not deform. Let's see, is that deforming too much or not enough? That's too much deformation. Right? We're just a little bit more stressed. Something goes really far. This is called the non-linear. It's just not linear. But people mix this up with elastic. Okay? This whole regime in general, in terms of material, is elastic. And elastic means it'll go back on the same path. So if you take it and you stretch it to here, and you let it go back, it'll go right back to zero. You stretch it to here, right back to zero. You stretch it to here, right back to zero. Now if you stretch it past into the nonlinear regime, it'll still go right back to zero. It'll follow its nonlinear behavior right back. It doesn't matter that it's nonlinear. But if you go here, beyond the elastic regime, then you get into plastic behavior. What that means is you've now damaged the material. Okay? It is not the same material it was back when you never went into the plastic regime, but now you have. And how's it going to go back? Is it going to go back this or go back that? Think about it in your head. You don't know. It's going to go back like this. And what has happened? You've stretched it. Right? This is your O-wing T-shirt from 2 years ago. Right? It was here, and now it's here. Okay? With no stress, it's got a permanent strain. Right? So that's what plastic. That's a plastic deformation. That's why plastic materials are called plastic, because they deform plastically. So plastics are plastic all the time. It's hard to get them to do anything plastic. Linear, either one. It looks like I wrote regime, which is a little formal and militaristic, so let me write region. There we go. Linear region and the non-linear, not linear region. That's how things behave. And then, another question, there's one more, is where will they break? The tensile strength is where it will break. It's sort of how much delta L over L can it take, and at that point, how much stress will you apply? And then it'll be gone. Right? Then it's broken. Usually, in an engineering problem, you don't want to take something to here because you've plastically deformed it. Really, this is kind of where you want to be, but then to be safe, of course, they say don't go past here. Nobody wants the bridge to collapse. Let's all stay down. Okay, but technically, it doesn't break until usually after it is plastically deformed. Let's see. Well, there's all kinds of questions here. Where did the pie come from? And the emoji has like a pie on their head. Where did the pie come from? Oh, this is the area, pi r squared. Why did we add a kilogram? Because we wanted to see it stretch. So the other fun thing you can do, and you come after class and do this if you want, is you can feel the regime. You can feel the springiness, but if I push this hard enough, I should go into the plastic regime, right? Ooh, should we? How long has that been bolted up there? Because if that ever falls on me, that would be bad. I'm pretty fast though, so y'all give me a heads up. That's right. Okay, it's at 53. What? Oh, look at that. We plastically deformed it. It's at 40. Is it still metal? Yeah, it still vibrates. So if you want to plastically deform a wire, come after about to go. What? You kind of have to say that. What? It's not going to fall. This thing holds a bowling ball. I'm not pushing that one. So there's still 30 centimeters of deformation to go. So each of you takes half a centimeter. Each of you gets